on last week. So it's related to these silicon photonics micro-ring resonator modulators. And then there's also different bands of these modulators. I think the results we did look on was O band, which is 1310. In this case, 1311.4 nanometer laser wavelength, and in these bandwidths, in this band, uh, the modulated bandwidth is smaller than for C band. So that's why we can achieve smaller speed in North King and PAM4. And I also have a slide about how this bandwidth looks like. So this is S21 parameter, which describes the bandwidth. This is an electrical parameter. So here we see two different curves with 3 and 6 dB detuning. So for these modulators, what you do, you basically so so basically you have a laser here, and then your ring is modulated up or down, and then depending on where you put your bias, so the tuning, so whether you are here, which would be like uh, minus 3 dB or minus 6 dB. The bandwidth in this point will be larger and 6 dB will be smaller. But if you are in 6 dB, then you will get the more extinction ratio on this range. For example, on this range here, than on this range here when you tune when you would tune the resonator. So for C band devices, this bandwidth was around yeah, here is the C band where it was on a 3 dB point was close to, well, beyond 67 gigahertz. Okay, just for comparison, then we will move on to there are also some results, some typical curves like bit rate versus received optical power and different speeds. So for if the speed is smaller, then we can get better signal quality, so smaller bit error ratio, so less errors. And here we have graphs for on-off King, which is 2-level modulation format, and then there's a graph for PAM4, which is 4-level modulation format, and also representation in eye diagrams. And what we can see that this opening here, for example, for 206 is much smaller. There's also many transitions coming also in the middle. Like compared to this one, this eye diagram is cleaner. So this is just not quantitative. It's not quantitative but qualitative. Uh, uh, how to say, evaluation of signal quality. And yeah, so and for PAM4, then you have multiple eyes, and the eye opening is much smaller. That's why when you look at the bit rate, of course, it's not the same symbol rate, so it's very difficult to compare. But the bit rate is similar. So PAM4, yeah, maybe yeah, it's difficult to say which one is better in this system. Depends on where this modulator would be used. There is also some graph of performance of digital decision feedback equalizer. I will not go too much in details on this one. We have also for two different speeds, for on-off King and also for PAM4. Right. So then there's a result which we presented last week. So this work actually is going to be presented in Silicon Photonics conference in 2 weeks, or it's quite soon. So my PhD student is going to present this result. So here we tested the Mach Zehnders. So let me come back to this slide here. So I was showing you results with ring resonant modulators, which are located here. But here we are talking about Mach Zehnder modulators. So these are larger, 2 millimeter long devices. This is 5 micrometer. So yeah, but this you can drive with differential signals. So and also yeah, so it offers more bandwidth. Um, so if we go back to this graph, so then we see that the bandwidth here is like 5 dB, also beyond 70 gigahertz. We didn't measure farther out, so we don't know. But by seeing by the results, so we managed to achieve even 256 gigabaud on of King, which is more than with rings. Um, and also we did the test of different temperature ranges on the chips. So right. Okay. So that's eye diagram. That's when we don't use an amplifier. So that's like 300 gigabits, I think the highest we achieved. And we also have a result where we use an EDFA, I think here. And then we can reach 350 gigabits with silicon photonics modulators. Which is rather high. So we're looking forward to this conference to see what is the newest achievements, not only from our group but from other groups. Right. Okay. So then the last modulator I wanted to cover from intensity modulation direct detection, it's silicon germanium electroabsorption modulators. We talked about electroabsorption modulators in previous lectures, just different principles of modulators, how they work. So this particular electroabsorption modulator works that if you put a light through the semiconductor material and you apply voltage, then the absorption of material changes. And this absorption coefficient is used to modulate. And it used the Franz Keldysh effect. So it's very fast phenomena. So then one can do quite high speed modulation and low power consumption. So the one big problem there is self-heating of this modulator. What happens is when you put in more power, this transfer function shifts to a different wavelength. And since this particular chip we tested on wafer with the grating couplers, these grating couplers, they allow you to couple light to modulator, but they are also wavelength dependent. So imagine if you have a transfer function for modulator which shifting to higher wavelength with a different temperature, then your grating coupler starts to filter away your power, total optical power you can put in. So it's kind of trade-off there. And this is like integration of germanium silica on CO2 wafer. So yeah, these I think is the modulator with the largest bandwidth we have seen so far in this in silicon photonics with integration with germanium. But I think the fastest results we still managed to achieve with the Mach Zehnder, if I'm not wrong. So let's look. So in this case, we have to use an EDFA because I mentioned of this self-heating effect and then grating couplers not being optimized. Well, they're being optimized, but the bandwidth is limited. So right. So we see that it's quite flat response with some frequency dips, and again it's measured up to 67 gigahertz. It's just curious how how it goes further. So maybe in future tests we're gonna look into this. So what we did was 160 gigabaud PAM4, so it's 320 gigabits. 256 gigabaud on of King was rather good performance. And here is also different DFE configuration analysis. Right, so with Maxander we managed to achieve 350 gigabits with DFA, so that's our highest achievement so far with silicon photonics modulators. Right, so then these tests on chips, unfortunately, currently we do not have a automated probe station in Riga Technical University. We have a home-built station, but we have a very good relations with Keysight Technologies, and we have students who are doing internship there, and we usually do these tests in their premises a couple of times a year. So we kind of collect chips from our collaborators, and then we perform the testing of those chips. So sometimes we test chips we are not allowed to show. So that's why I have here this CO2 crystal image, which I took from in Washington, DC. I was in Natural History Museum. It was a Silicon Photonics conference, which happened in 2020, I think, two. And then I presented the results of a chip which we were not allowed to show. So I put this image here, but you can see that it's pretty high speed on of King. I think that time was 240 gigabits per second on of King. So we managed to increase that number quite a bit. So yeah, but it's a good opportunity for us to collaborate because we get access to equipment which sometimes is prototype and not available in market. So that's quite unique opportunity for us in the field. So with this slide, I wanted to finish intensity modulation direct detection direct detection topic. And then I think it's time to move on to second part of this course, where we look in coherent, digital coherent, optical communication systems. And these are used for longer reach. So there are different optimization which needs to be done. So and yeah, so it's all about systems capacity. And these are, for example, links that are, maybe I should go back a little bit to a map where we could talk about. Yeah, I think here. So we are kind of moving now to from intra data centers, from passive optical networks. Well, some of them passive optical networks are becoming coherent already, from front haul discussion. So we look more in backhaul, in metro edge, long haul transoceanic links. So this is what we are going to focus on now, and try to see how you can get even more capacity. Well, with of course with some complexity, but using coherent modulation signals. So so we didn't invent much in optical domain. So we took what was already available. So the new generation optical transmission systems are advanced digital radio systems that has changed to optical frequencies, like these all modulation formats over different years, from 1991 to 2001, like from OFDM, CDMA, QPSK, DMT, and also quadrature amplitude modulation. And you see that these different systems have been using these modulation formats, and most of these modulation formats are now used in optical communication systems. So why would you like to use these advanced digital signals. So not only multi-level and amplitude, but in coherent systems you have access to other parameters. So, but it's also important to remind us also about equation, which is kind of setting how much signal we could transmit, and I mean this is related like to two basic parameters, so signal to noise ratio, and what is the uh, what is our bandwidth in the system. So it very much depends on signal to noise ratio, what type of signal to noise ratio we have. So so yeah. So and this is assumption if we have only wide Gaussian no additive wide Gaussian noise. And yeah, so so what the basic trade-off is that you can increase if you have this high signal to noise ratio, then you can increase capacity and you don't have to increase the optical bandwidth. So if you don't, if you cannot increase the pulse rate, or which is symbol rate, then you can increase the number of symbol alternatives. And so here, as I mentioned, there's also other multiplexing possibilities, because in coherent systems you can use I mean, there's a number of degrees of freedoms, and one very early used was polarization division multiplexing. So, so moving to coherent signals, you have also more degrees of freedoms which you can utilize. Right. So if we look in just a basic coherent communication system, so what we have is the big change is that in the receiver, we also have a laser, which is not modulated. And it's called an LO laser, so it's local oscillator laser. So basically, it is supplied into the receiver, and it provides a coherent receiver gain, because you have this whole local oscillator power, so you can easily get 10 dB gain. So so basically, what this allows you to do is to have quite small signal level here, and you still can get quite good signal sensitivity. And the difference also that since you have these more degrees of freedom, so it's not only intensity, but you have intensity and phase and polarization that you can do. So in IQ modulators, I believe I will have some IQ modulator later on. I mean, I could draw it just for the sake of better understanding. So basically, what you do is that you have two branches. It's like then you have a one Mach-Zehnder modulator, which is you modulate amplitude here. Here you modulate amplitude, and then you need to have a phase modulator as well here. So because you modulating I and Q, so you modulate complex signal. So here you need to have a shift of 90 degrees. So so basically, you can put on one modulator, you put on off keying signal with like two levels here, and you put two levels here, and then you need to rotate this to this condition. So at the output, you get the 4 points of QPSK. So and in this way, still your symbol length is the same, and which means that here you have a 2 bits and you have 2 bits. So So you can double the capacity just by adding this additional. So yeah, bit more complex modulator here. So uh, you get four points. You have four symbols, and then yeah. So like in on of king, so you would have uh, one symbol, one bit per symbol. Here we have 2 bits per symbol, because you have one symbol here, one symbol here. It is the same symbol, but you can represent 2 bits. So we will have a bit more detailed on these on different on different number of bits per constellation size. So, but let me just clean the screen. Right. So what we have here is that I was talking about INQ data. So it's one non-return to zero signal, other non-return to zero signal. They are shifted because you need to have INQ. And I was talking about in phase and quadrature. So we have a 90-degree shift in these signals. So when we modulate, we have in phase and quadrature signals. So we have two signals, and then we can recover I data and Q data. So yeah, so we can get double amount of data, and then we need to see how many bits we have here. Right, so it's 1 bit per symbol, so it's uh, 2 bits here, 2 bits there, so it increased the capacity. Of course, it adds of complexity, because you need to also have a bit more complicated receiver structure. But right, so so we looked at this I diagrams in the intensity modulation direct detection systems. For on of king is 2-level modulation format, and then for PAM4, when you have 2 bits per symbol, then you have I diagram something like this. But then in coherent single carrier signals, they are normally represented with constellations in I and Q planes. So what happens that you have in phase, which looks like this, or rotated by 90 degrees, the I diagram. And then there's quadrature, which is, as we see, the same as here. So those two are combined together. So here you have a transitions between the symbols, and then now you have 4 symbols, but you have 8 bits. So basically, with this representation, you have managed to achieve already twice the capacity for the same bandwidth. So and if the signal to noise if the signal to noise ratio allows, then you can put even more signals. For example, not 4 points, but you can have 16 points, and then you have 4 bits on one symbol. So you increase the capacity by factor of 2 again. And that's why it's easy, for example, to get on smaller band, or on the same bandwidth, more capacity, like it's done with PAM. But in coherent systems, you have another degree of freedom, because you have in phase and quadrature. That gives you another factor of 2. Right, so here's some practical I diagram, the constellation diagram we took in some experiments when we are doing still research on coherent digital optical communications in Sweden. So that was one typical I diagram. It's quite old already, so currently you can get much better 16 QAM constellations. Well, depends on the signal to noise ratio, of course. Right. But it's not everything. So you can add more levels of multiplexing. One thing is that you can also use different states of polarization. So in addition to these 4 bits per symbol, you can double it again, and that gives you like 16 QAM with 4 bits per symbol in one polarization, and 16 QAM with 4 bits per symbol on other polarization. So because we have two principal states of polarization, X and Y polarization, and this polarization division multiplexing is really like you have if you have orthogonal polarizations, that means that there's no crosstalk between polarizations, almost no crosstalk. So it's also an independent channel. And when you have this polarization division multiplexing already, well, so you have coherent modulation format. So you have IQ data, then have polarization division multiplexing on the same wavelength. You're already having 8 bits per symbol. Then what you can do more is that you can have multiple of these lasers and multiplexed and demultiplexed in wavelength division multiplexing systems. And in coherent communications, it's really big development was amplification in specific bands. Because currently C plus L band is actively used for longer reach systems. So and quite high number of bits per symbol. Then something I have not touched upon here is also different type of constellation shaping. So that I think I'm gonna talk a bit later. So then I think we had already this graph. It's some from paper from OFC 2014. So now we have even higher generation of these coherent systems and higher capacities. But yeah, so that was in 2014 that you are in second generation. Well, now it's digital coherent. It is. We have super channels. That's already has happened, and there are more updates. I can probably bring a more recent curve. But what was done in a way is that first was a single channel systems, then was 5G, then was like 2.5 gigabits times 8, 2.5 gigabits times 16, and then these 10 gigabit systems were scaled up from 16 to 192 channels. And then another jump was when the symbol, the bit rate per wavelength was increased to 40 gigabit per second. And then it's, but these still were intense stimulation directed edge. There was also other modulation formats like phase shift keying and so on. So yeah, so right, and then it was 100 gig. For 100 gig, we are talking about 1.6 tera, 3.2 terabits, and so single channel experiments, I think it was rather high in recent demonstrations, showing quite high data rate in terabits per single wavelength. Right, so here we come to different number of degrees of freedom. So I already talked about quadrature, that you can have different types of constellations, like from QPSK, 8PSK, 16 QAM. So that gives you a degree of freedom. Then there's also this polarization, what we touched upon, that polarization multiplexing. There's also polarization modulation possible. Then you can also modulate with different codes, with different frequencies, and also modulate with time. So you can do time division multiplexing. And one increasing research topic, it's really a space division multiplexing. Now in recent years, we also see that first multi-core fibers are being deployed. So that in this case, so we have the same outer diameter. So we have a single mode fiber. It has 125 micrometers. And then you have for single mode fiber there's one core which is roughly 9 micrometers, something like that. What you can do is you can keep this 125 and you can put two separate cores or four cores or more cores. So these are like multi-core systems. So this is when you add another dimension to increase the capacity, for example, with quadrature, polarization, and space and frequency, wavelength division multiplexing. So and within this quadrature, you can also still do time division multiplexing. Right. So one interesting fact why the space division multiplexing systems are very interesting is that so so if we imagine transoceanic cables, so let me just go back to some map with cables. Here, for example. So we have quite a lot of transoceanic fiber optic cables, and to install these cables, it's done with ships and robots. And the main thing is that every ship has a limited capacity of how much cable could be, how long cable can be installed. So the diameter of the cable is the same. So then by moving into these moving deeper into so if you can decrease the size of a fiber, that's a very good thing. Let me just go back to the slide. Here, if you can reduce the if you can still keep the same size, 125 microns, but add more cores. So basically I have four independent fibers here. So which means that your cable capacity is again multiplied by a factor of 2 or 4, and that's a big gain if you are laying down transoceanic cables. You expect to deliver capacity, and capacity means money. So then you can factor 2 your income from that cable. Right. And then there's also one more thing what you can do. So when you do these wavelength division multiplexing systems and you are operating communication systems with different generations of these wavelength channels. For example, it can be a situation that there's 10 gigabit, 40 gigabit, 100 gigabit, 400 gigabit, and terabit coexists in one fiber. So then there's different approaches how you can do with how do you allocate these different how you allocate channel spacing. So there's a fixed grid, 50 gigahertz, 100 gigahertz, 200, 400, and then there's also a flexible grid. Then you are mixing together different systems. So there are different pros and cons. I mean, with flex grid, you probably get better spectral efficiency, but there's always like a link performance and whether all these different signals are how to say having the same having good enough performance for these links. Right. Okay, but then there's also another possibility for this flex grid. It adds a bit of complexity because complexity, but also it adds a possibility to have also these mesh type of networks where you have several links connecting to a single node. So there's typical like ring and mesh, and nowadays even we are talking about mesh networks in free space optical communications in the air. Like big player Starlink is installing these. Launching, I think currently there are 7,000 satellites flying, which are being used to deliver broadband services and also used for dual use purposes. Right, so yeah. And then here's also some visualization how these different wavelengths could be done. So here's different switches, how you could switch different space channels. So this is just some physical realization how different elements like from fiber array, you just front end optics, you just make it from diverging, you make it how to say collimated, and then you have a diffraction grating that which is used to switch different wavelengths here, and then you have some reflector. So your channels come in and then they come out in different ports. So yeah, so input port, output port. So you can do switching in these mesh networks, and that's very a nice thing to do. And so you can have these wavelength selective switches, which is based on so you have reconfigurable optical add drop multiplexers in these mesh nodes, and then you can switch these different channels between different ports and different links. So that's gives a lot of how to say lot of flexibility and how you want to route your network. And for example, if one link fails, then you can reroute all the critical traffic to different routes. I mean, there was recent cuts in fiber optic cables in Baltic Sea, so all the traffic was rerouted to a different route, not going through that particular cable. So I think ROADMs were used to perform the job, right? Okay, so then if we look into different modulation formats, so we see how much bandwidth does these take. For example, you have some fixed grid, so on-off king with 10 gigabits, and if we compare on-off king with 100 gigabits, then for 100 gigabits you need more bandwidth, otherwise these channels start to interfere, but you can still deliver the same 100 gigabits by using QPSK modulation format and use the same 50 gigahertz grid. So it's now a lot of different works how to get higher capacity with this limited grid, and there are other methods which could be possible. So right, so here's just a comparison that for on-off king, you have a simple hardware and both transmitter receiver, but it's very much impacted by chromatic dispersion and polarization mode dispersion. And for coherent modulation formats, you have a more complex hardware, but then you get more narrow spectrum, so it has a lower impact from chromatic dispersion and polarization mode dispersion. And in addition, these coherent optical modulation formats and coherent detection, you get access, like in intensive modulation direct detection systems, you get access only to intensity. So there are limited things you can do with digital signal processing. So, but in coherent modulation formats, you really modulate amplitude and phase. So you have both amplitude and phase information, which gives you more freedom to do digital signal processing. And you can easily also compensate for chromatic dispersion with coherent in with the digital signal processing in coherent after coherent receiver. So that's been shown and demonstrated, and links up to 10,000 of kilometers have been demonstrated in loop experiments in also practical systems. So right. So how do we get? So here is like 100 gigabits. 100 gigabits of data if you use a non-return to zero on-off keying. So you get the first zero is around 100 gigahertz. Then if you go to QPSK, you narrow the spectrum factor of 2 because now you have I and Q. So you can use 50 gigahertz of data. Then what you can do, you can add one factor of 2, so you can squeeze this 100 gigabits and use only 25 gigahertz. So in this case, it's 50. In this case, it's already 25 gigahertz. What you can do I mean, because you get factor of 2 from QPSK, factor of 2 from polarization division multiplexing, and what can you still do? You can still use not non-return to zero shape, which is something like this, but you can use a pulse shaping of these shapes. So basically, this is uh, this is I think we had very nice example, drawn example with pulse shaping in IMDD. So it's basically root raised cosine pulse shaping. So I'll try to go back and find the image. Sorry, it takes a little time. Right here, for example, that your non-return to zero, this is how it looks in spectrum, and this is more rectangular and in time domain. But if you use a roll of factor of 0.01 for root raised cosine, so your time domain signal looks something like this, but your optical spectrum is more square-like. So you can pack one more channel here and one more channel here. And basically, you can probably put like more capacity with pulse shaping than with non-return to zero signal by using the same band. So basically, at least you can double the capacity by if we look to the first zero. If we don't, I mean, we don't count these. If we count the energy only here, then you can double it with the pulse shaping. Right. So let's go back. Okay, so this is just a good visualization for what can be done to achieve the same 100 gigabits of data. So and yeah, and that's impressive from different generations of communication systems. How you can get to these narrow uh, narrow optical spectrums, but still delivering 100 gigabits of data. And of course, you need a certain signal to noise ratio to do that. Right. Okay. Then I think we already have this slide, so I'm gonna skip it. So I wanted to look a bit more on constellations. So that intensity modulation direct detection systems, if we look in constellations wise, then on-off keying looks like two dots here on a, so I and this is Q plane. So on a real plane we have two dots, and then on imagery plane we don't have any because we don't really modulate the phase. What we do that from on-off keying we can get to QPSK, and from QPSK if we add more levels we can get 8 PSK, so we have 8 phase levels. So right, but we can also modulate not only So here we modulate only amplitude. Here we modulate only phase. So we have the same amplitude for all points, but we modulate the phase. But then we can modulate both amplitude and phase, and we can get from 16 QAM to 64 QAM. And then these constellation points, I think I don't have a specific slide on probabilistic shaping, but I think I should mention here. So for example, you can also choose that you transmit more often these symbols and you avoid to transmit these symbols because uh, these are affected more by nonlinearities because it's more power sent. So you start to you get different effects. I mean, we are going to talk about uh, nonlinear capacity limit, but that will take either this week or the next lecture. I think we are talking quite. I think we need to take a short break and then we come back after the break. So is that fine?
Yep.
Recording stopped.
So are you back from the break?
Yes.
Okay, then we have we have covered that you can modulate both amplitude and phase, and this also gives increase in capacity. So here I just have a slide where we can see how many bits per symbol we can get. So from BPSK, which is like on of king would be like at zero, as point at zero and point here, but you have like same amplitude, but you have two opposite phase, like uh, binary phase shift king. Then you can have 1 bit per symbol. With QPSK you can have 2 bits per symbol. 8 PSK you have already 3 bits per symbol, and with 16 QAM you have 4 bits per symbol. So we already covered this. So but what what is important here also, like if you go from on of king to pump 4, pump 6, pump 8 and higher levels, what happens here, that here have a quite big gap, you also have a quite big gap, and here you don't have any gaps, and here you have very it's a quite low signal to noise ratio, so it's difficult to say all the 16 points, like these symbols here, where do they belong? Either they belong this side or this side. So yeah, so if you have a signal to noise ratio, then you can go for higher order modulation formats. If you don't, you need to go for lower. Yeah, so that's one way how to do it. Yeah. Okay, so I think we already covered quite well the EDFA in previous lectures. So that's one of the ways how to amplify the signal and continue with the how to make the links even longer. Right, so there's just some visualizations that these gains for EDFA depends also on input signal. And this is for a specific amplifier, like if you have a higher input power, I mean, there are different signal depending on the signal power, the input power and output power. So the gain varies for the amplifiers depending on in yeah signal power and power M. So what is also important that the gain spectrum, this is a typical for C band. It's also similar to the noise figure here. Yes, right. And then these amplifiers, they can be put in different distances. So when you don't have enough power, and then you put an amplifier to get the amplifier increased. And what happens is that whenever you amplify the signal, you also add a noise figure by each amplifier. So what happens with your optical signal to noise ratio? It's usually starts to decrease and decrease quite significantly. So if we talk about optical signal to noise ratio, then if we have optical spectrum, and then you have it here. Then here is your noise level. But then you want to measure, when you do the measurement of optical signal to noise ratio, you want to measure the integral power here. So you measure one integral power here, and then you need to estimate the noise level here. So do estimation, and then you need to convert it also to that is on the same resolution, and then you can you know what is the noise level and what is signal plus noise, and then you can calculate what is the optical signal to noise ratio. I mean, sometimes engineers, they just looked at the difference between signal and noise. It's not easy to do in WDM systems when you have one more channel here. Then there's different methods how to estimate the signal to noise ratio, like you can switch off and on the signal, or you can know what is the shape of the signal, and then if you know the noise level, then you can get OSNR if you know how the signal should look like. Right. So yeah, and then there are different types of amplifiers, as I was trying to mention in the previous slide. So these, it depends what input power you can have and what output power you will get. So you can have a booster amplifier. So in this one, you put quite high input power, and preamplifier, you put quite low input power, and you get not very high power, maybe plus 5 dBm here. Here you maybe have plus 20. Depends also on nonlinearities. Maybe it's can be plus 10, and this one can be 0. So it depends on how many channels you have in a system, because it's these wavelength division multiplexing systems, also single channel systems, depending on the power, these can become more nonlinear. Okay. And nonlinearities, I think we will cover in some later slides that there are different types of nonlinearities which affect in a fiber. So I think in later slides we're gonna talk about that. But yes, so the big problem with the distance is that optical signal to noise ratio decreases with every amplifier. You add noise. So basically, at the link start, maybe you have something like, I don't know, 40 dB signal noise ratio, but after 10,000 kilometers, maybe it's 16 dB. So, which means that at this signal to noise ratio, maybe you can transmit 64 QAM, but here you can only maybe transmit QPSK. uh, so, so yeah, I mean, your available signal to noise ratio is really setting up how much capacity you can do if you don't change the symbol rate. Right. And we can also look on if we have a 16 QAM or QPSK. So these OSNR curves. So as I mentioned, that bit rate, depending on OSNR, some theoretical values for QPSK, you to get, let's say, hard FEC somewhere here. So you need 14 dB of OSNR. So what I said previously, so most likely 16 dB, you can run QPSK there. Because then you're somewhere on this quality level. So you even have a bit of margin here, like 2 dB margin. But in order to run 16 QAM at so sorry, hard FEC is somewhere here, somewhere here. So in order to run 16 QAM at hard FEC, then you need something like 18, almost 19 dBm. So that's 90 dB optical signal to noise ratio. That's much more. So we have these typical curves in intensity modulation direct detection systems. We only look in receive power. We don't look in noise because those are not amplified systems. So there we are mainly limited by receiver noise, and of course some noise from the laser, but mainly limited by the receiver noise. So here we are also limited by amplifier noise quite significantly. So optical signal to noise ratio for a signal, it's very important to see how it is. And also here you can see that until hard FEC somewhere here, we can transmit maybe close to 6,000, below 6,000 kilometers. But with QPSK, we can go even well beyond 10,000 kilometers. Right. Then there's next thing we need to look into is how much light we have in optical fiber. So it's like a field distribution in optical fiber. and we kind of can calculate what is effective area of this fiber where the light propagates, and then this yeah, so then this for example for specific link length, I mean we have uh yeah we have a specific link length, then we have a normalized power, and how the power drops. If we amplify it, we have different types of effects. I mean, we can uh, get different types of effects. For example, here we have a normalized gain spectrum of generated stimulated brilliant scattering and has a Lorentzian shape. And then we have this gain spectrum generated by stimulated Raman scattering on single mode fiber if you pump it for 1430. So there are different other effects which happen in a fiber. So one is brilliant scattering, other is Raman scattering, and Raman scattering is one is a nonlinear effect, but it also thanks to its broad nature. So here we have, I mean, at the peak we at least have some 5 terahertz. So this can also be used as amplifier. And this, by changing these pump wavelengths here, you can use it to have build different fiber amplifiers to amplify the signals. Right, but stimulated brilliant scattering, it's only like 100. Here we have, this is like 100 megahertz. So, and you kind of get, when you pump quite high uh, signal power into the fiber, you will get a tone of brilliant scattering, and it can go both ways. And it's difficult to compensate for this one. So, right. And Raman scattering, if you have multiple channels, then channels at 1430 will start to amplify. So basically, your data channels will provide the gain for other channels in this, depending on how far is the distance. Right. Okay, so there's other things. So when you have a also you can have other type of nonlinearities. One is scattering. Other type is nonlinearities like self-phase modulation and cross-phase modulation. So self-phase modulation is with the pulse with the channel itself. So what happens is that you start to generate new frequency components here, and so in single channel you basically so this is how you can tell that this is nonlinear effect, because you start to add new frequency components, and here this is the way that the spectrum becomes broader. In cross phase modulation, that you start to get one signal starts to modulate the other signal here. They both become broader, but they also affect each other. So right. And then there's one more, which is four-wave mixing, and it's rather bad if you, for example, have a zero dispersion in a fiber. It was very hard lesson for in Japan when WDM systems were installed, and they kind of thought, okay, dispersion was the problem, so they decided to design a fiber with a dispersion, with a zero dispersion in the WDM system, and it created very good conditions for four-way mixing for Kerr effects. So and what happens that from 3 waves you start to generate already several degenerate and non-degenerate components. So basically you start to get 1, 2, 3, 4, 5, 6, 7, 8, 9 different combinations, and this is a combination between this guy, combination with this guy and this guy, and then you start to do combinations between these two as well, and so on. So this spectrum can become even wider and wider and wider. So, and this is a disturbance. And the problem is that this disturbance is a copy of a neighboring channel. So this is like interference on the same wavelength. It's very difficult to compensate for these kind of uh, effects. So yeah, so you kind of with coherent systems, you have a lot of freedom that you can get better signal quality, better higher capacity, but it comes at a price. Like like we were talking about from 1 of king to PAM4, the signal to noise ratio, the eye opening drops like 3 times. So in this case, when you put more channels and you put quite high power, then nonlinear effect starts to limit how many or at all you can transmit the data on these channels. So one clever way how to solve this problem was to put multiple channels, but you put one here, you put one here, and then one put more farther closer like this. And if you design these channels in a specific non-even way, then you can land all these components somewhere here in the middle. So basically you can filter them out. And that was the way how they fixed in. So of course it reduced the capacity what you can use, but still then your fiber is not wasted. You can still transmit more data than just a single channel. Right. So that's another impact, and this is quite critical. So these nonlinear effects are limiting capacity in standard single mode fibers. So like we were looking at this equation which sets a capacity in linear case, so you're limited by noise. But and then I think I will have a graph later on, but it just illustrate that the capacity is like from SNR, but then due to nonlinearities, you start to drop at some rate because this is due to non-linearities here. But I will have a graph later on with a better illustration. Right, then there's other effects like polarization mode dispersion. So what happens when you have two orthogonal polarizations? And the problem is that fiber is not really regular in a sense that it's birefringent depending on different lengths, and that relates to how fiber is manufactured. So you basically start to get differential group delay in different polarizations, and right. So and it's really it's really like a different distribution. It's not very so it's very different, and you need to look in. Sorry. So and then it's very different, and you really need to look in statistics to get what is the mean and how large is the standard deviation on this effect. Right. So then there is this graph I mentioned about, which is capacity. So information spectral density and power spectral density. So how much? I think I will. Do you have a question? If you don't, so maybe I would just like to mute. Okay. Sorry. So then there's like how so the linear transmission would go like this, and due to nonlinear effects, then you start to degrade because you put more power into the system. And direct detection, you don't get some so high spectral range, but you also get limited by nonlinear effects. Right. So with coherent, you can still do something. You get higher because yeah, there are different ways how to do this, and right. So we're gonna cover some of them also later on. Uh, Right. So this higher spectral efficiency. So we looked in that you can get better tolerance to fiber dispersion. This is because you can make the spectrum more narrow. Then you can use higher symbol rate for a same wavelength channel grid. Sorry, not symbol rate, but higher bit rate because you use higher order modulation format. So you get multiplied by several factors, and the bandwidth it can be for electronics smaller, and for modulators also can be kept smaller. But of course, now systems that are being commercialized in coherent are going to be already 260 gigabaud, and the sweet spot of modulation format would be like something around 16 QAM, but with probabilistic shaping. Okay, so here is the graph capacity versus signal to noise ratio per bit, and this is really yeah, you kind of start to get limit. You cannot approach the channel limit, and the different tricks you need to do to go closer and closer. I don't think you can get here because that's theoretically impossible. But we'll see how it goes on. Currently, it's not being demonstrated, but you can get pretty close here. And very interesting fact that this optimization here, it costs quite a lot of money because of submarine cables. If you can, using the same system, add another terabit, it is quite a big revenue stream. Okay, here's again constellation diagrams, different types. And there's one interesting number you can keep in mind, that the minimal signal to noise ratio is to transmit information is minus 1.59 decibels. It just some it's a negative signal to noise ratio, and you can already start transmit information. Right. Then what happens, as I told, there's these nonlinear effects which limit how far we can transmit, and these nonlinear effects uh, decrease the transmission. So these nonlinear effects increase with the distance for 8,000 kilometers. So basically, the nonlinear effects, they accumulate quite a bit, and then, for example, for 500 kilometers, we can transmit still 30 dB signal to noise ratio and get quite high spectral efficiency, like around close to 9. But then if we do longer distance, then the spectral efficiency drops, and signal to noise ratio, which we can do, we cannot pump more, because then the so then the nonlinear effects start to play a role. So what can be done is that this effect of nonlinearities can combat, and there's like uh, for many years they used Monaco equation to model optical link and to calculate how far distance and what type of effects will be in a system. And then when these analog to digital converters become quite powerful and DSP, then you could actually use not compensate only for chromatic dispersion, but try to do a digital back propagation. So this is quite interesting approach, that you need to guess how the fiber looks like, and along the way how the nonlinearities were added to the signal. So you can do a digital back propagation, so you can back calculate and calculate away all the nonlinear linear effects and get back to the pulses. So this is quite interesting approach and demonstrated several times. We also try to use it in the lab, so it's quite fun to see how you can use the simulation in a tool to get in real in experimental system to get better signal quality. Right. So then these capacities, I think this is already quite old figure. So from 2011. So in a single core fiber over 165 kilometers, it was 100.1 terabits per second. So what did they use was 370 WDM channels with 25 spacing and they used C plus L bands, which is 10.8 terahertz, and each channel divided in 4 OFDM subbands. Right, so then it's like what type of OFDM symbols were used, like 1 megabaud 128 QAM, and then you have over 4 times 550 OFDM subcarriers per channel. Then you get polarization multiplexing, and then you kind of multiplex. You get around 294 gigabits per wavelength channel. So you get spectral efficiency of 11 bits per hertz. But then it was done in not in real time. So it was a post-deadline paper from OFC 2011. Right, and then this spectral efficiency over the years has been increased and it's still being increased. And capacity like WDM channels, but here is another trend here, which is called SDM, spatial division multiplexing, which gives another feedback. So yeah, I probably should have updated this graph as well with more new information. Okay, and then yeah, so this is what I was drawing here, that you have this spatial division multiplexing, and here is one example. It was in 2012. Actually, it happened to be that I was in DTU doing my 3 months of doing my 3 months of Erasmus exchange in Technical University of Denmark. So I managed to be at the same time with Professor Toshe Maroke in Denmark. So he just recently moved to Denmark from NTT. And that was a year when they showed 1 petabit. So I was probably, yeah, so that was the year later they did 1 petabit over 52 kilometer multi-core fiber. So yeah, Professor Marekes, he's still in DTU, so still working on SDM and getting higher and higher numbers. So, but this is quite impressive data rates. What could be achieved over 12 core optical fiber, multi-core fiber, and very interesting is how you couple it from these multi cores to one core. So fan in, fan out element. It's quite critical. So they used 5.7 gigabaud 32 QAM signals and spectral efficiency 12 times this 7.6 bits per second. I think I'm gonna end with this because then we're moving in more other impairments and on more about the bits symbol allocation. So I think the only thing what I wanted to remind you is that next week is Easter holiday, so there are no more lectures, and I'm not sure whether Daria is here. I think she was busy with with lab preparations for our faculty evaluation. So I think I will stop recording for now. And then I'm here to reply some questions if I can. Otherwise, if you have questions about practical works, then you should reach to Daria directly. And yeah, so do you have some questions? So if there's no more questions, then you can slowly start leaving.